I'll start. So as it is written here, next week it's on Wednesday. So what are we trying to do? So if we start from a phi gamma module D of rank 2, over OE, then we constructed some representation pi of D of GL2 of QP. So it's a unitary representation. And then we were trying to describe the locally analytic vectors of this representation. So there is one abstract description that is useful, which is due to Schneider and Teitelbaum, which says that to get the locally analytic vectors, what you do is you start from the dual of pi of D. Then you use it as a module over the completed group ring of some of any compact subgroup, I mean compact open subgroup. Then you attach the scalar to the distribution, and then you take the dual. So another way to say a thing is that if you take an element in pi of D, which is going to be the dual of pi of D dual, then it is locally analytic if and only if it extends as a continuous, as a continuous linear form on this space. Okay, and the key point is the study. So the key point of this description now is the study of this operator WD, which goes from D cross ZP star to D cross ZP star, where WD is just the restriction of the element of the Weil group to this space. And the result I mentioned last time was that, well, this space here has a very nice structure as a gamma module, so action of gamma. And so I remind you the theorem that I mentioned, and I even almost gave a proof. So if you start from OL double bracket T, then you can construct a ring OE, which is just obtained by inverting T and completing. Okay? So if you do the same thing with OL of gamma, which is essentially procyclic, you get a ring that I called OE of gamma, meaning that you take, well, you take in the generator, you invert, and you complete for the p-adic topology. And the theorem that we proved was that this module D cross ZP star of gamma, D cross ZP star, so in general, not only in this situation, so has exactly the same invariant factors or elementary divisors, has the same elementary divisors as on an OE of gamma module as D viewed as an OE module. No, here it's true in any situation. So whether you are torsion or non-torsion. And so in fact, so we are going to use it more in the case where D is free. So if D is free, of rank D, then D cross ZP star is free of rank D over OE of gamma. And as I mentioned, this is one of the key results that allows you to recover Tate's Euler Poincaré formula from the theory of phi gamma module. Okay, so now inside of D cross ZP star, there is some sub module which Fontaine calls the heart of the phi gamma module. So it's serving something I call C because in French it's cœur, and cœur starts with a C. So C is the module, this module. So you start from D psi equals 1, and you take its image by the operator 1 minus phi. And so when you apply psi to an element here, you get 0, because psi phi is equal to identity. And so you get something which is in D cross ZP star. So this is inside a D psi equals 0. And this is nothing else than D cross ZP star. So if you have a phi gamma module, you can also look at the heart of the Tate dual of your phi gamma module. And then there is a lemma which is easy to verify, is that C and C Czech are exact orthogonal for the pairing. Well, the pairing is defined as on D Czech cross D with value in OL or L mod OL, depending whether you are torsion or torsion free. But as I mentioned to you, in fact, this pairing localizes, so it also gives a perfect pairing on D cross ZP star and D Czech cross ZP star. So you take the restriction to D Czech cross ZP star cross D cross ZP star. So they are exact orthogonal when you restrict it to this one. Okay. So that's quite not difficult to verify. And from there, you will be able to give a nice description of the structure of this C. So maybe I should point out that by construction, because gamma commutes with psi and phi, these are gamma modules. So, okay, so you have action of gamma, stable by gamma. So the proposition is the following. So it's a construction of some natural pairing that in fact comes from Iwasawa theory. Because I remind you that this module here is closely related to Iwasawa theory by a result of Fontaine. And so the pairing that you can build is the following. So you start from an element X in C Czech, an element Y in C, and some N in N. Then you can define some element Vn, which is, so you choose some representative of ZP star mod P to the N. And then you look at the following expression. So I'm going to define what this tau n here. So I'm going to explain what this is. Sigma I times x, y, times sigma I. So what are these objects? So gamma n is a generator of gamma n, which corresponds to 1 plus p to the n zp. And this tau n is just an isomorphism between gamma n and p to the n and zp. So tau n of sigma a is just defined as log of a divided by p to the n. I think that's it. And what does this mean? So I remind you that, well, because we have a structure of OL of gamma module, you can actually invert gamma n minus 1 on this module, and then it gives you, so this is an element of OL. And so what does it say? So that's a definition. But so the point is the following, is that if you look at the sequence of Vn, yeah, so what I should say is that this Vn is well defined. So in lambda of gamma modulo gamma n minus 1. Okay, so here you made some choice, but when you mod out by gamma n minus 1, you get an element which is well defined. And so what you can prove easily is that in fact you get a compatible system. And so this defines an element of lambda, which is just a projective limit of lambda mod gamma n minus 1. And what is this lambda mod gamma n minus 1? It's just OL of gamma modulo gamma n. Okay, so here maybe if I want to get into OL, I have to assume that I am torsion free. Okay, otherwise you have to replace it by L mod OL. So this pairing is equivariant, meaning that you have the following thing. So, and this Vn, so you get an element which I called, so it's a pairing of xy, and I put an Iwasawa here because it is coming from Iwasawa theory. And so what you get is that sigma x y Iwasawa, so it's antilinear with respect to the first variable and linear with respect to the second one. Equals sigma of xy. So that's for all sigma in gamma. And finally, which is, so I mean this is just purely formal. And the thing which is not formal and which follows from this lemma is the fact that you get a perfect duality in this way. So Iwasawa identifies Ch to Hom over lambda of C in lambda. Okay, so you really get a perfect duality. And so this last thing as a consequence, which tells you that C, so assume that where C is free, that's what you get from this thing. But if D, where C is free of rank D, if our D that we started with was free of rank D, over lambda. And what you get also is that this OE, this D cross ZP star, is just equal to OE of gamma tensor over lambda C. So what this produces for you is some free lambda module, so something which has absolutely no denominator in gamma, which generates your module here. And that's going to be extremely useful. So maybe before we use it to attack locally analytic vectors, let me make you some connection with Iwasawa theory. I don't remember exactly, but this was in Serre's paper on Iwasawa, in Serre's Bourbaki report on Iwasawa, on Iwasawa's work. When you take the B dual of something, you get something which is free.
So we're saying C is free or C check is free?
Well, it's the same because you can.
It identifies it both ways around.
Yeah.
I think.
Sorry. Yeah, I wanted with C check, but I mean you can just shift the role of D and D check, and maybe C is free and C check also. C and C check. So link with Iwasawa theory. So as I mentioned before, so you have this result of Fontaine, which tells you that this deep psi equals 1 is what I call usually H1 Iwasawa of the Galois representation attached to D. And what is this module? Well, you can define it either as the H1 of GQP with value in lambda tensor V of D. But it is more often presented at the projective limit for co-restriction of H1 of G QP, where you add P to the nth root of unity with value in V of D. And I mean, this isomorphism is just Shapiro's lemma. I mean, basically. So, I mean, most people prefer to use this description, but sometimes it's very nice to have this description because you have only one Galois group, I mean, one cohomology group and not a projective limit of groups. Now, you have this exact sequence. D phi equals 1 goes to D psi equals 1 goes to C. And the map from here to here is just multiplication by 1 minus phi. And this is just isomorphic to V of D fixed by GQP. By, no, sorry, not by GQP. It's V of D, phi equals 1. GQP of mu p infinity. Well, anyway, so what you get is something which is finite dimensional as an OL module. So it's a torsion lambda module. So that's a torsion lambda module. And so this exact sequence here, and with this isomorphism, gives you an interpretation or decomposition of this module. So you have a kernel which is the lambda torsion that you can describe explicitly, and then you have a free module of rank the dimension of your representation, basically. So that was used by Pierre and Ryu. And now, what is this pairing here? Well, if you start from an element X in C, or in D psi equals 1, let's say. It will not change anything because the pairing is going to kill the torsion. Then because of this isomorphism, you get a class Cn of x here at each level. So Cn of x, which is an element of this thing. Okay. And same if you start with a y in d ch psi equals 1, then you get a class Cn of y. And now what is the interpretation of the thing I wrote over here? Then what you prove is that this tau n of gamma over gamma n minus 1 yx, this is going to be exactly the cup pairing of Cn of y with Cn of x. So it's a cup pairing in in Galois cohomology with value in H2 of Zp of 1, and then you get so, and this H2 is isomorphic to OL. Okay, and so why do I call this Iwasawa? It's because the formula that is here is exactly inspired by a formula that Perrin-Rioux uses all the time in our work, and I think it's quite classical in Iwasawa theory. Okay. So once this is done, we can attack the action of WD on D cross dP star. So it's a little bit painful. Huh? So I remind you some notation from probably the first course. So if we have an integer b bigger than 1, we define nb to be the integer p minus 1, p to the b minus 1. And we define an rb to be 1 over nb. So this is the periodic valuation of primitive p to the bth root of unity. And then we define some ring OE dagger b to be, well, you start from OL double bracket t, which is just OE natural. Then you invert a little bit t, meaning that you add p over t to the nb. And then you complete, separate and complete for the periodic topology. Okay, so you get power series with value with coefficient. I mean, no, you get Laurent series with coefficient in t and with an exponentially small on the left. So they converge on some annulus, and then we define the 0 RB to be the same thing, but you invert t now. And then, so I'm not going to define all the rings, but we also define some ring which we call RA RB. So I mean the notation, as I remind you, are supposed to give you on which kind of annulus these series are converging. Okay, so RB with something like this means that it is converging for it is converging up to RB, up to valuation equal RB. And when you have something here, it means it's not converging for valuation 0, but it is bounded when you approach valuation 0. And we also define some rings that we call E0RB. So the difference between this and this is that it's not bounded when you approach 0. And so we define some big ring. So E dagger, which would be the so you invert T and you take the union of these things, and you add R which consists in taking the union of all these things. And inside here we add this ring R plus, which is also R natural. Okay. So now we do the same thing on the level of phi gamma module. So you start from D, an element in phi gamma étal of OE of rank D, and you define a sum module D dag B. So it's going to be the biggest sub OE dag B module of finite type such that there is not too much denominator in T, and not too much denominator in T, it can be translated in this way, so such that when you look at his image by phi, then this is inside the module generated by D dag B, but that's not possible. But you have to add OE dag B plus 1. So I remind you maybe that phi of OE dag B is inside OE dag B plus 1, and so on. So the coefficient, I mean, because phi increases the denominators, it makes the annulus on which everything converges smaller, and so the best thing that you can hope is something like that. And so you have to prove that such a thing exists. And in fact, well, I give you an intrinsic definition. So that's the definition you would find in Charbonnier's thesis, for example. But I mean, if you really want to work with these things, it's better to define them in terms of Fontaine rings. So I'm not going to give the description in terms of Fontaine rings because I won't need it. But if you actually want to prove statements, it's much better to think of them in terms of Fontaine rings. So this D dagger B would be defined as some A dagger B, where this A dagger B would be some subring of A, tensor V of D. And then you would take the fixed part by the Galois group of the cyclotomic extension. Okay, and and so basically, what you do is that you always work in this ring here to prove things. Okay, so that's a definition. But I mean, nothing tells you that this is non-zero, for example. And so the theorem that we proved with Charbonnier is the following. What?
Is it clear there is a largest one?
It's not clear. Nothing is clear. It becomes clearer if you write it in this way, in fact. So the theorem that we prove with Charbonnier is that there exists some integer m0 of D such that well, this module is big enough, meaning that if you start from D dag m0 of D, then you can recover D by extending scalar. So, and here you have to take the tensor product over yeah, so that's the first thing that is true. And the second thing is true, which is true, is that for all b bigger than m0 of d, yeah?
So is d dagger b free?
So it's going to be free for b big enough. For the smallest one for which this is non-zero, I mean, yeah, so no, it's not always free. Yeah, but when you increase b, it's going to become free. So if b is bigger than m0 of d, so in this m0 of d, in fact, I have assumed that, I mean, I took m0 of d big enough so that it becomes free. b bigger than m0 of d, then it's true also that d dagger b can be obtained from d dagger m0 of d. Okay, so in fact, you can take, as I said, m0 of d such that this module is free, and then all these modules are going to be free generated by this thing. And so once you have done that, well, you can just define modules d0rb. What else? d_rb, d0rb. Well, this one is going to give you a d-dag, and this one is going to give you something I call d-rig. So by just, you take this module and you tensor by the appropriate ring. Okay, so I give you just one example. So e.g. d0rb is equal to O0rb e tensor d dag m0 over O dag m0. Okay, so you have a whole list of things. And what is true is that this d0rb is going to be equal to the intersection over all A of d RA_RB, where you invert P. So you invert P, L times, and this D ring is just the union of D0RB, exactly as the ring were satisfying this kind of thing. And then, so what is useful to know is how this how these submodules are respected by gamma and by phi and psi. So what is clear basically is that gamma respects everything. And now the problem is that phi increases the denominator. So what you get is that phi sends d dag b into d dag b plus 1. And the same, it sends d RA_RB inside d RA plus 1 b plus 1, RB plus 1, and so on. Okay? And now psi goes in the other direction. So that's for all b bigger than m0 of d. I mean, what I wrote here would be okay also for b less than m0 of d, but basically you would get 0, so it will not be very interesting. And psi goes in the other direction. So psi of d dag b plus 1 is going to be inside d dag b. And for this, you really need b to be bigger than m0 of d, and so on. And so one thing that you see is from this thing is that all this map, so yeah, so all these rings are stable by the operation restriction to I plus p to the n zp. which I remind you is just 1 plus t to the I, phi to the n, psi to the n, 1 plus t to the minus I. And so if you really want this to be true, you need n to be less than b minus m0 of d. So you need that b is bigger than n plus m0 of d. Just because this psi sends you to m0 of d, but then when you apply n, well, sorry. Maybe I should just put b bigger than. No, that's okay. Okay. So now we need the action of gamma again. And so, well, as I say, if you start from OE, which you can view as the Iwasawa algebra of ZP, then you get this ring OE, but you get also all the other rings. Blah, blah, blah. So if you start from gamma, which will be OL double bracket gamma, which is lambda of gamma, well, I told you that you can construct this OE of gamma, but you can also construct all the same ring where you add a gamma here by the same construction. You just replace T by a generator of gamma. So let me give you one definition, and then you will see how to do the rest. So you choose D bigger than 1, such that gamma D is isomorphic to ZP. So for P equals 2, you would take D equals 2, for example. Then you are going to define OE dagger B of gamma D of gamma to be lambda gamma tensor over lambda gamma D. Sorry. Of the ring OE of dagger B minus D of gamma D. And now this gamma D here, because it is isomorphic to ZP, then you get the definition you would think of. It's lambda gamma D. Then you invert P to gamma minus 1 to the NB, and then you complete. Okay, so I mean there is just a shift here because yeah.
Is lambda sub gamma the same as lambda parentheses?
Lambda sub gamma is the same. Yeah. Sorry. yeah. How do I call it usually? Lambda k. Well, I mean this is the same thing. Yeah, so you have to do that because this gamma is not exactly isomorphic to ZP. So you have to choose a subgroup which is isomorphic to ZP, and then just extend the scalar to get a gamma algebra. And now the theorem that is proved exactly as the previous one is the following. So, yeah. Well, no, let's. So it tells you that there is some bigger integer, m1 of d, or m2 of d, such that the following is true. Well, in fact, when you look at D0 RB cross ZP star, then this is obtained from the heart of the module by just extending the scalar from lambda, which is lambda gamma, to this ring OE 0 RB of gamma. So I remind you that if I remove everything here, that's the theorem I proved last time. And so this is still true if you add some convergence. Yeah, and that's true for B bigger than M1 of D. Okay, and once you have that, well, you prove the same thing with D0 RB. And here you would have OE 0 RB of gamma. And then by taking inductive limit, you prove the same thing for D rig. D rig cross EP star, and here you would have R of gamma. Okay, so the point of everything here is that everything is controlled by this module C. Okay, so if you want to be able to describe the action of WD, you just need basically to understand what happens to C. That's the idea. Yeah, and maybe I should say something is that these things are very useful in Iwasawa theory to produce what we call explicit reciprocity laws. So, so why do we introduce this kind of overconvergent elements? It's because this overconvergent element is exactly what allows you to go from the world of Figma module to the usual world of Pierre-Colmez theory using lasering, Biederam, Bicris, and so on. So in fact, maybe I should say that this ring here is exactly the ring, the subring of element of the ring A, which is inside the theory of Figma module, which is such that when you apply phi minus n, phi minus b to one of these elements, then it actually converges into Biederam plus. So it means that this module you can send into this ring you can send into Biederam plus, and so the modules D dagger B you can send into something which is built out of Biederam. And we will see it next time. Yeah, and then using these kind of things, well, you can, and using the deep C equals 1, then you can actually transfer information from the computation in Galois cohomology using Figma modules to Biederam, and that's how you get explicit reciprocity law, just by expanding the formulas. So what is the main point? Now, it's the following. So main point is the following proposition. Is that when you apply, so you have to define something, sorry. So we have our C, and which is 1 minus phi d psi equals 1. Then we define delta alpha to be delta of P inverse. So delta D of P. So maybe I called it omega D so it's a central character. It's the determinant of D shifted by, so maybe it was omega D, I think. Yeah, so omega D of X is x norm x minus 1 times determinant of D, viewed as a character. It is exactly the character, well, maybe I called it delta D, I don't remember. I mean, the character that you use to construct the module D cross P1. Yeah, and so you define C prime to be 1 minus alpha phi d psi equals alpha. And so this is still inside d psi equals 0, which is d cross dp star, as we said before. And so basically it's the same module as C, except it is for the module that you would obtain by twisting your phi gamma module by the character delta D. And twisting by the character delta D just gives you an isomorphism between D and DH, because we are in dimension 2 by delta D minus 1. Okay, so the proposition is the following. Is that when you apply WD to C, well, you get C prime. And when you apply WD to C prime, you get C. And why is this true? Well, if you take an element X in C, so by definition, it's a restriction to ZP star of an element which is invariant by psi. But being invariant by psi means that you can put, yeah, so maybe I should say something like this. So this produces some element X tilde in D cross QP. So what you do, you first start by lifting X to an element of D psi equals 1, and then an element of D psi equals 1, you view it as an element of D psi equals 1 just by sending it to X. Okay? I remind you that these things just mean that you have sequence of elements which correspond by psi. And because we are, yeah, and maybe I assume that D is irreducible. So in this case, when you do that, up to some bounded torsion, you get also an element, well, it's not completely true. If you invert P, it will become true. And then, what you can do still, you can lift X tilde to an element in D, to an element in P star, in pi star, sorry. So wait. If I want, so it will be pi star tensor omega D. So pi star omega D, which is just isomorphic to D natural cross P1. So you have a map from D natural cross P1 to D natural cross QP, which is just a restriction to QP map. So this map has a kernel, which is very easy to describe, and it is surjective. And so you can lift it. And so what you get, because you had something, you started with something which is fixed by psi, you get an element here which is invariant, so fixed, so x hat, and x hat is fixed by P001. So that's exactly what corresponds to the fact that your X tilde that you started with was fixed by psi equals 1. Now if you apply W to this X hat, you're going to get an element which is transformed by the central character. So it will be fixed by Wx hat is fixed by 1, 0, 0, p. You just conjugate. But 1, 0, 0, p is just p minus 1 up to homothécy. And this homothécy, the element in the center, they are acted upon by a central character. And the central character is just omega d. Okay? And so what you get, you take your Wx hat, you restrict it to Zp star, and that's exactly the image of W of x by your Wd. And so because you have something which is fixed by that, then you get into C prime. So this argument bothered me a little bit for a while because I did not see for a while why it would not work in general, in fact. Even if you put the wrong character for the construction. But in fact, so I checked, I can only prove that this map from here to here is surjective only in the case where where this thing is really fixed by G. So there is no contradiction in mathematics there. So. Well, anyway, so what you see appearing in this picture is the following triangle, which plays a big role, but I mean, it does not play an actual role, but it plays a big role in a background role. So I told you that you have this d psi equals 1, which is isomorphic to H1 Iwasawa of the V. And now we just saw that this is also isomorphic to pi star, well, maybe up to a twist by a determinant, fixed by P001. Okay? And as I told you, in this isomorphism here, so it's hidden the construction of p-adic L functions à la Perrin-Rioux. So this isomorphism knows about p-adic L functions. So this is some local factor p-adic L functions. So basically, it knows about epsilon factors and so on, except that I don't know how to extract them from here. I mean, basically, I know it knows them, but I don't know how. And so what you see here is that you can also, I mean, the p-adic local Lagrange correspondence give you an interpretation of this Iwasawa module in terms of representation of GL2. And so that's what is used by Emerton and his collaborator to study this kind of module. Okay. So what do we get as a corollary? Well, corollary is that if you can increase m1 of d still a little bit, and then you get something like that. So there exists some m of d, which I call m, with the following properties, such that d0rb cross zp star is stable by wd for all b bigger than this m. So how do you prove that? From what we said before, Well, first you use two things. You use the fact that D0RB cross ZP star is nothing else than O E0RB gamma tensor C. And then you use the fact that this map WD is semilinear with respect to the action of gamma. And why so? It's because, well, if you apply W to the matrix A001, well, what you get is A0, 0A times A minus 1, 0, 0, 1 times W. Okay? And so if you translate this into an action on D cross ZP star, so you get on D cross ZP star, what you get is that WD composed with sigma A is equal to delta D of A, sigma A minus 1 composed with WD. Okay? So what you get is a semilinear action. So you get that the action of WD is actually semilinear with respect to the action of gamma. Yeah, but now this is also equal to the same thing with C prime. Why so? Because C prime is exactly the same thing as C, but for a twist of the phi gamma module by some character. And so you see, and it's also clear that WD. Wait, what do I want to say? No, I don't want to say anything. It's clear that the map that sends sigma A to delta of D of A sigma A minus 1. So this gives you a map on lambda. So it gives you a map on lambda. And it gives you an involution on lambda. And it gives you also involution on these strings for if B is big enough. Okay? And so using all this, well, because C is sent to C prime, then you see that this one is sent to himself. Yeah, because what is the problem? Well, you need delta D of A to be close to 1 if you want to invert it. It cannot be so far from 1. So, I mean, B big enough, it may be bigger than 2 or something like that. So. Yeah, and so as I said, you cannot use, we have an explicit formula for this WD, but you cannot use it to prove anything fine. And as you see, I mean, to prove that this submodule is stable by WD, we have to go around. I mean, we never use actually WD directly. But we use the fact that we know that something inside is stable by WD. Okay. So what do we get from this corollary over there? Well, we're going to get a big something. So the first corollary that we get is the following proposition. Is that if you look at D0RB cross P1, so by which I mean the sub module of D cross P1 where the both entries are in are in D0 RB, well, then this is stable by GL2 of ZP. So if B is bigger than M. And now when you take the union of all these things, so this D dagger cross P1, this one is stable by G. And how do you prove that? Well, it's just you go back to the skeleton of actions that I define. And so, well, probably you don't remember, but I had explained to you that this formula were just used to prove that some submodules of things were stable by G. And basically what you have to prove, yeah. For this one, for example, it's formula of skeleton of action and the fact that this D dagger is stable by phi, psi, gamma, and so on. Okay, and then now what you do is that you are going to extend the scalars to D rig. So you extend WD by linearity on D rig cross ZP star, because this D rig cross ZP star is nothing else than R of gamma tensor over E dag of gamma of D dag cross ZP star. And so once you have done that, you define D rig cross P1 as usual to be the set of Z1, Z2 in D rig cross D rig, such that, well, same formula as always, the restriction to ZP star of Z2 is WD times the restriction of ZP star of Z1. And then I claim that this comes with an action of G by the skeleton. So yes, skeleton of action. So how do you check that? Well, I mean, your G is a quotient of some big G tilde. So the skeleton of actions gives you the action of generators of G. But there is no a priori condition that ensures that it factors through an action of G. Okay? So you have to prove that the groups that you get from these generators, and no relation, where the kernel of this map is going to act trivially. But it acts trivially on a D dagger cross P1, and which is dense in there, and so by continuity it's going to act trivially everywhere. So in this way you get an action of G. Okay. And then the main theorem is the following. And then in the next hour I explain to you how you prove it. So let me remind you what the dictionary of periodic functional analysis is about. So we have this exact sequence, continuous functions star, and dual of continuous functions goes to E, goes to continuous function and ZP goes to 0. Inside here, you have the analytic function, locally analytic functions. And when you take the inverse image, you have the ring E dagger, which is inside here. And here you have still the measures. And now when you extend the scalar to D rig, to the row bar ring, so this sits inside the row bar ring, which surject onto locally analytic functions. Here it's equal. But here, what you get here is the dual of locally analytic functions. Okay, so the theorem says the same thing for pi of d, the theorem. So by construction, we have the following exact sequence. So you have pi of d dual, tensor omega d, goes to d cross p1, goes to pi of d, goes to 0. So inside here, we have this d dagger cross p1, which I just explained to you that it was stable by g. And then its image here is exactly the locally analytic functions. So the dual is still the same. And now this one, you can view it as a sub thing inside D rig cross P1. So this still surject onto P onto the locally analytic vectors of pi of d. And now the kernel is the kernel of the locally analytic vectors, tensor omega d. So the theorem is that you have a diagram like this with an action of G everywhere. Okay, so maybe it's a good point to stop before everybody falls asleep. And